Hello and welcome back to the Mocap Toolbox Workshop Part 2. Marc and Hartmann is going to tell us about the latest release features and advanced features that are available. Now, take it away, Marc.
Thanks. So, well, welcome everyone. Maybe some of you were not in the first part of this tutorial. So just briefly, I wanted to say that yeah, so the Mocap Toolbox is available in GitHub. You need MATLAB and hopefully a recent version of MATLAB. Like yeah, the fresher the better to use it. There is actually a wiki page in the Mocap Toolbox page of GitHub. So if you enter here, you will find well, introduction and related information, general information on the toolbox. Then there's gonna be a run through the different types of functions that there are, and also there are examples, some of which are used in this tutorial. This tutorial is a modified version that also includes some newer functions of those examples, and then it explains the different data structures and parameter structures that Marc was introducing before, and also it allows us to understand, all those WKs and so on that are a little bit cryptic. So here you get some detailed information on that, so that you can actually create, for instance, the animations that you want. Like for example, with the anim bar, the animation parameter structure. Here you can know, for example, with colors, that this is a 5-character string, or it can be also an RGB triple that contains the colors of first the background, then the markers, then the connections, then the tracers, and then the marker number. So all of that you can modify. And then in function reference, you actually find all the functions and examples also of basically the syntax that you would use to call them. So you can easily find the functions here. Well, in MATLAB you can always use the help command, but maybe this is a nicer looking way to kind of the same information, to get the same. It's also easy to just search for a function like mcread, and then you will get there easily. Okay, not so easily, but maybe it's best to just click here and find it, and then you go, okay, and now it's found. All right. How can I get rid of you? How was it? Hide floating meeting controls. Yeah, it's good. Okay. Then I also wanted to show that some extensions and add-ons have been developed over the years. For instance, Christian Numoen, he used to be here and created this MC array, which basically adds functionality for basically when you have like a large set of data, like you have multiple recordings or something like that, then you can process them all at once without the need of including loops in your code and so on. Like you don't need the for loop right here. You can just have an array, and then it'll actually go through all the recordings inside that array. And for example, eye tracker syncing between Mocap data and eye tracker data. So yeah, pretty useful stuff there. But yeah, we're not getting into that. I wanted also to briefly show you some examples of new functionality like for instance, yeah. So for instance, we have this type of animation which creates it animates the movement data just like Marc did it, but you can also animate time series data. It can be a line plot or an image that is actually coming as you're as they are dancing, so as to see what is happening while they are dancing. Like for example, here you can modify this to make it a little bit more meaningful, but this is going to tell you that they are interacting at a frequency of 2 Hertz, also every now and then at 1 Hertz, this type of stuff. And it's pretty useful. You can also specify whether you want this data to be animated here or here or here or here or everywhere. So then Marc also showed how to have a lot of vegetables in the background, but that doesn't need to be an image. It can be a video that you can use as an input, and then yeah. So if you use a video, then you can create things like this. So you can have a you know a nice. So this is actually markerless movement data that we're having. So it has been analyzed using OpenPose, and then from OpenPose to the Mocap Toolbox. Okay, this is another example that quickly came. But anyway, so yeah, this other example I wanted to show as well. So so also Christian Numoen has come up with a 3D NCPlot frame, which is this function to create to visualize the mocap data, and also well, for animating it like this. So if you want to have this fancier version, yeah, this is already there in the Mocap Toolbox. So you can I'm not gonna get into that, but you can have a look at it yourself if you're interested. I'm not showing it because it's a little bit of an experimental feature, because well, it's implemented, but we need to sort it out in such a way that when you run NCPlot frame and this other function called NCPlot 3D frame, you would get the same camera view, which is not the case. So yeah, we need to sort certain things out, but still it works perfectly fine. And by the way, this is markerless data. We have used Theia 3D to obtain estimates based on video data. So we have an array of video cameras, and then we use yeah, AI to estimate the pulses in from each of these recordings, and then we get from Theia information about the location, but also about the orientation of these different joints that are estimated, these anatomical landmarks. And so in Mocap Toolbox, you can visualize this position data, but also the orientation, right? So that's why you have all these red, blue, and green colors to understand how is the orientation with respect to a global coordinate system to the origin, which is somewhere in the floor usually, right? Okay, so that I wanted to show you. And all right, so I think I can now continue with the demo. I actually have generated some of these animations so that they don't take too much time to compute. Yeah. Oh, by the way, interrupt me whenever you want. You know, even if you're somewhere in Zoom, just go ahead and talk, so that, yeah.
Which function was it that gave you the interaction video?
Yeah. Okay. So
Can you go to below this file? Yeah, this synchrony video.
Oh yeah.
Or yeah, which function is it that gives you the frequency plot?
So this is the generalized cross wavelet transform, which is a generalization of the cross wavelet transform, which is well, it's kind of akin to the cross spectrum. So it's a pointwise multiplication of two spectrograms, in this case, two wavelet transforms. It has very interesting properties. I'm not going to get into that, but yeah, you can obtain that in the Mocap Toolbox. So okay, I'll go straight there because yeah, it's somewhere in the bottom. But if you search for thank you, GXWT GJ, then you can actually obtain this type of visualization. Yeah, it's recommended to start from velocity data. I will get into that later. Anyway, if you have used Mocap Toolbox, then maybe you know what I'm talking about. And then you just compute this generalized cross-wavelet transform between one person and the other person, and then well, you can specify other options there, and but that will give you a complex representation. So you will have if you want to visualize it as it was there, then you can take the absolute of that. So then the generalized cross-wavelet transform magnitudes, and yeah, use a function called MC animate data in order to animate both the movement and this time series, this multivariate time series that we get. Okay, but where were we? So we were creating animations with a perspective or three-dimensional effect. So if we want, we can create an animation without this perspective projection, which will look like this. So you see that this guy is walking towards us, but it's not getting bigger and bigger and bigger as it walks. So basically, the location of the camera is moving together with that person. Whereas if you okay, you can change here the name of the file that you're gonna create, and then you set perspective, this option to 1. Is it big enough, by the way? Yeah, okay. I can make it a little bit bigger, but somehow, well, anyway, yeah, so then it's gonna create an animation that okay, that it's called pairs 1, and it looks like this. So it's getting closer to you and then leaving. Yeah, pretty neat. Yeah, so basically you can modify the parameters. They are in this field. So it's the parameters. For example, where is the camera going to be? So here in pairs.c, you can specify, okay, you know, in the x-axis is going to be 1 meter away from the global coordinate system, and so on, right? And then you can animate it. So if you change the position, then yeah, you can get a different video. Different looking video, and so on. All right, so now what we do a lot for movement data analysis, so not anymore for visualization, but when we want to analyze data, we usually don't want or or subjects to you know, to move all over the place, because if you know, if we're moving, that's very natural, and that's how free dance is. But then you cannot really understand you know, what, for example, how much the hand is moving, because it's moving relative to you know, the location of the whole body, right? So you want to tear these things apart, and yeah. And also the other problem is that the global coordinate system is somewhere there in the floor, right? And so, you know, if for example, that my position data might be negative or positive depending on where I am located as a dancer, or whatever I am, right? So in those cases, then we want to do some sort of transformations of the data, right? We want to also distinguish the movements that are mediolateral from the movements that are anteroposterior, which we cannot do if the dancer is rotating, you know, which so we have to move the global origin to somewhere in the body, right? So that, you know, that there's going to be some part of the body that is going to be 0, 0, 0, and then other parts of the body will have then the coordinates translated based on that. Yeah, so, and rotated and so on. Yeah, so if we want to center the data at 0, 0, 0, then we can use MC center, right? So then basically the idea here, okay, would be to clear the data. Then we load again this data, and then we can trim it, and then yeah, then we can use this function that will center that data. So it's so if I remember correctly, it centers it in such a way that the geometrical mean of these points is 0, 0, 0, geometric mean. But maybe Marc and Petri can correct me. Yeah. So then here, okay, we have a different version. Okay, it's not necessary to use a different version, but well, we have here mapr.1 as a new version of this animation parameter structure, or this mocap structure, and then we have modified the colors here. Oh yeah, it is necessary, but because we're going to have one animation parameter structure for one person, and then another one for another version of that person, right? Then what we are doing is using MC translate to translate one person by 1 meter with respect to the other one on the horizontal plane. And then we use these two parameter structures to differentiate between these two. So there's going to be a white person and a green person here, because we have changed the colors for one of these two. And then we can plot frame number 200, right? Oh, sorry. And then we merge these two. Yes, we have merged these two representations. So D and DC, which is the centered version. Yeah. All right. So yeah, so that's the idea. So D is going to be the centered version of the of this person, and then DC is going to be just a translated one. All right. So then we can also rotate the data by some angle. It is by default rotating around the vertical axis. So here we have a global coordinate system somewhere. So, you know, if this is the vertical axis, then it's going to rotate like this, right? But then you can rotate it in any way you want. And so, okay, here we're using the same idea. So we're actually showing the effect of the rotation with this green subject. All right. Then with MC to frontal, we can rotate the data so as to have a frontal view. And here you can choose what kind of frontal view do you want. So do you want the frontal view for each of the frames? Do you want each frame to be corrected so that you get a frontal view of the subject, or do you want to get a frontal view in average? So if you know, so in that case, it's gonna kind of look like this, pure data, if you have dance movement data. So yeah, so it's gonna be like that, and so this is gonna be useful in order to understand what is happening, you know, with these mediolateral movements, and to be able to distinguish them from the anteroposterior ones. Here we are defining a frontal plane. In order to do this, we need to tell what is going to be the frontal plane that is going to be corrected all the time, so that you get a frontal view with respect to the to the location of the to the orientation of the camera. And so so here we have used the back hips, because you see that we are representing the waist with 4 markers here. So we used these ones to define the frontal plane, and here we use the frame option. So if you animate the data, you will see that, you know, it's all the time like this, right? It's doing all kinds of things, but then it's stuck there. Right. So then we, as I said before, we can do this coordinate transformation from a global to a local coordinate system. So this is using MC to local with the, so it's choosing the sternum to be the origin here. It's going to be 0, 0, 0. So the sternum will never move. It's gonna stay still. So don't expect to get any movement data from the sternum. And then the frontal view is going to be based on these front hip markers, right? So again, you have defined the plane, and you know that the sternum is not going to move. Yeah. So here, okay, it's creating it, right, an animation, and I'll show you how it looks. So it's like this. Yeah. So you see that the sternum is still, and you get this frontal view. But then here it's using this mean option. So you see that you see that the hips are actually rotating a little bit. Yeah. But not too much. So if there is this type of movement, you won't get it in the data. All right. Now we can move on to time derivatives, which can be computed from the Mocap data, and we can also visualize them. So, well, this is fairly simple, and Marc already introduced this idea. So MC time derivative will compute any derivative that you want, the first, the second, and so on. So it's basically diffing the data, so taking the difference between the subsequent time points, and then it's applying a low pass filter. All right, so here is it a low pass filter? Some smoothing. Yeah, and let's see if it, yeah, okay, yeah, it should work. So now we can use this function that Marc already introduced called NCPlot time series to visualize some of the markers, head, hand, and foot. This can be replaced by actual strings. And then on the third dimension, which is the vertical one. Yeah, so this is the position data that we have in dance2. But then in D2B, we have the velocity, and in D2A, we have the acceleration. So we can look at them. And yeah, what you will see easily is that velocity and acceleration are just how is it called? Yeah, they are basically zero crossing all the time, right? Yeah, so it's centered around zero. And then for acceleration, we will see the same. Yeah, because these time derivatives are kind of like high pass filters, then you're gonna get higher values as you get larger time derivatives. Yeah, so and then we can do different types of statistical analysis on the time series data. There is, for example, the possibility to compute the standard deviations for certain markers very easily. By the way, I mean, if you want, you can just do it from the data itself. So all the data is stored here in dance1.data. So so you can, this would be, if you wanted to just get the standard deviations for all the markers, that's kind of a faster, easier way to go. But the difference is that these functions are ignoring any missing frames. So if you might get not the numbers if you do this. Whereas if you use MC, STD, MC mean, and so on, then that takes care of the missing frames. So yeah, and you have this statistical moments, skewness, kurtosis, standard deviation. All right, and then you can actually do a windowed analysis as well in the Mocap Toolbox. So basically, you can specify a window length, a hop factor, and then compute standard deviation and see how the standard deviation evolves over time, the dynamics of it. All right. Then, okay, we will get into something that we use quite often, which is joint representations, and something that we use less often, which is segment representations. So the idea is that we have lots of markers, but sometimes we're not interested in all those markers. It might be that you have a marker here and then another marker here in the hand, and you want to just analyze what's happening with the hand. So you want to reduce that into one marker. So you want to average those two, right? And so you will get something that is somewhere in the middle of this hand, of this wrist. So yeah, if you want to do that, then you go from a marker representation to a joint representation. And okay, so let's start first with our walking person. So we have defined the colors. We want the marker numbers to be shown, the marker size to be fairly big, and the azimuth is basically yeah, it's doing this with the camera, so it's gonna tell, okay, the camera is going to be there, 90 degrees from where it originally was. Yeah, so here we can use this yeah, these parameters that we have in this variable called M2J par. So it contains the parameters for this marker to joint conversion. It contains the parameters that Walk2 uses, but of course you can modify this as you wish, right? Depending on how many markers you had when you recorded the data, and what you want to achieve, right? So basically, the important thing here is that, you know, you're, for example, defining the root, which is somewhere there in the center of the body, based on markers 9, 10, 11, and 12, which are those there that are hidden there in the waist, right? And you're defining the head from markers of 1, 2, 3, and 4, right? So all those will be averaged, and you will get just one joint out of those, right? So this you can modify as you wish, right? So you want to modify it, you just get dirty and start assigning things differently, right? You can set I don't know, you can set the number 1 to, let's say, I don't know, 8, 10. I would like, oh, sorry, like this. 10, 11, and 12, and that will modify the, in a weird way, the root marker, right? Just to give an example. All right, so here you have again this information about which markers correspond to each joint. So yeah, marker name 1, the root, marker number 1, these are the markers that will constitute the root. And then if you want to do the conversion from markers to joints, then you use this function that is called MC M2J. It has too many consonants, but so basically MC marker to joint, right? And then here you have the data, and then here you have this marker to joint parameter structure that you need for the conversion, and then boom, you have it. So Walk2J is now a joint representation, and it is different from the marker representation. You can see that okay, you have less markers here. Well, they are now joints, all right, and the data is also has been reduced because you don't have 3 dimensions per marker anymore. You just have one magnitude per marker. All right, so then if you want to visualize this joint representation, then you can create your own. You can, if you have used these particular parameters, then in MC demo data we have this joint animation parameter structure that contains already the connections between the joints, so that you have a nice skeleton there. And again, we can set the colors as we wish, having a white background and black joints and connections. We want numbers, we want large joints, we want the azimuth at 90 degrees, and we want to plot the frame number 160, right? And now it's a reduced representation. So this is actually quite useful when you are coming up with a manuscript. So because you probably don't want to, unless you're interested in what is happening, with I don't know, for example, in this case, unless you're interested in what's happening with the rotation of the head which is now lost, then you have the possibility to say, okay, what was going on with the head? Well, was the person head banging or not, right? So it will simplify your life if you don't have a lot of markers. Okay, so then next step is going to be to do a joint to segment transformation. Okay, so why do we use segments? Well, because we have people who have done research on for example, on the relative mass of different segments. And so this is something that we can assign, and based on that, we can look at the potential energy of different segments, right? So relative to something, for instance, relative to the floor, right? Or the rotational energy or the translational energy. We can also look at the angular velocity of different segments and so on. So if you want to do this, then there is a joint to segment parameter structure. And here you can see that we're not talking anymore about knees, for example. We're talking about thighs. So yeah, we have different names here. And here we're doing the transformation from the joints to the segments. Okay, so let me think a little bit. So how was the idea? I always get a little bit confused at this stage, but yeah, because basically you're defining the left hip segment. You want to specify what is the I have to remember. I always end up looking at the documentation to understand this. But yeah, so
the parent joint, the numbers are the parent joint, so it's like the
yeah. So I think the parent thing, the parent joint of the left hip is going to be the root, which is here 0, if I recall correctly, right? And then the parent joint of the thigh is going to be oh yeah, so, or was it that it has no parent? I'm sorry, I cannot remember how this goes. But because I use it so rarely.
where it says it's like 0, 1, 2, 3, 4. So it starts from the midpoint and then to the left hip thigh. So it goes like this. So it goes 1, 2, 3, 4, and then 1, 2, 3, 4 again. It's the same segment, and then it goes up.
That's that's right. Yeah. Yes, that's how it goes. Thank you so much, Marc. Yeah, exactly. So yeah, so left thigh and sorry?
Something like that.
Okay. Well, this is very well explained in the documentation, I must say. But anyway, so first you have you basically use parameters that are going to have to give you unique segments, and then you can apply this Dempster model, which is again telling you about the relative mass of these different segments with respect to the center of gravity of the body, and here you're grouping together these different segments, because the relative mass of this joint will be the same as the relative mass of this joint. So anyway, so that's basically what you're doing here. You're getting a new set of segment parameters that are like that, and here here you can see what the parameters are about. For example, this is the relative mass of each of the segments. And then you can compute the potential energy for each of these body segments. You need both the joint and the segment representation. And oh, I didn't compute it here. All right, and so yeah, so here you get it
I'm just
for each time point.
in the interest of time, maybe we should skip to like one video.
Right. Yeah. So the idea that we had was to get you started with this, and of course there are certain things that are so advanced that we cannot explain, but yeah, just to go through this. Anyway, so yeah, we can get the translation and rotational energy for each body segment. They will go to this trans and rot outputs, and if you want, actually doesn't work in this live script, but if you redo this in a command window of MATLAB, then this will work. It's going to animate the data together with the translational energy of each of these segments. Sorry, the total translational energy for each of the time points. Then, okay, another thing you might want to do is to do some dimensionality reduction on the mocap data. So here you can, okay, again, load the data, trim it so that it's a little bit shorter, convert it into a joint representation optionally, and then calculate the principal component projections of that joint structure, and then yeah. So this will give you the loadings, the scores, everything you get from PCA, and so you will be able to know, for example, how much variance is contained within each of the principal components, and also it is possible to use the loadings and the scores in order to generate a visualization of each of these principal components and to understand what are the most relevant modes of movement of this of a subject, like this, and yeah, you should be able to plot these different principal component projections. Yeah, I'll move forward, but analogously you can use like basically the same logic, but with for example with dyads. If you have a dyad, then you can look at so there's functions for computing canonical correlation analysis and also projection to latent structures, which kind of are, well, projection to latent structures is a generalization of PCA to two sets of data, and canonical correlation analysis is also, it's quite similar. The difference is what they are. What are these linear combinations that you're getting maximizing? Anyway, too much detail, but these are things that you can do in order to study the interpersonal synchrony between two dancers. Yeah. Then, okay, we can compute different movement features, like the cumulative distance that is traveled by a marker. For 3 different markers, how many meters have been traveled by different markers, and then yeah, the distance. What is the distance between the different markers at each time point? Is also possible to do, And you can also get this bounding rectangle, so the area that is covered within a determined period of time. So you need some window here for this function. All right, I'm not getting into the details. And there is a newer function that is called MC bound vol. So it gives you the bounding volume for each time point. So it's as if the subject was kind of wrapped inside a bag, and then you get the volume there. So it's useful if you want to look at whether the postures are open or they are closed. Also the area corresponding to that volume in the floor. That's another possibility. Yeah. Then you have measures of fluidity or smoothness of the data. So it's the ratio between the velocity and the acceleration. You also have the rotation range between two markers. Yeah, that's also possible to compute. And also a movement complexity or the dimensionality of the movement. So again, this is based on the eigen spectrum, right? So it's connected with this PCA, NCPCA function. All right. Also, it's possible to estimate periodicity using MC period. So this is based on autocorrelation for a given marker. It's gonna look at how periodic is the movement, and you can set the maximal period. So in some cases, you will not find any period for certain body parts or certain movement directions. Okay, we can. Yeah, in this case there isn't, but then if you increase the maximal period, then you will get some value there. Yeah, this is how it looks like. You can also compute the enhanced autocorrelation, which is going to reduce the effect of some of the integer multiples of the basic period. So here you will get a peak at around 2 Hertz. Okay, and quickly, so interpersonal synchrony can also be computed here. So here we're loading joint representations from recordings of a dancing dyad first, and that's how it would look like. We can animate that data. I think I have showed you that same animation before. It's the one that has the generalized cross-Wavelet transform. You can look at how synchronized dancers are at different frequencies with this generalized cross-Wavelet transform. So here you can see there's something going on at 2 Hertz and something at 1 Hertz. And you can also bring in if you have music that they are dancing to, then you can bring in that information, and then you will get a representation that is relative to the beat. So here you can see that, okay, they are mainly at the musical tactus level. They are synchronizing there. Yeah. Whether this is social synchrony or individual rhythmic synchrony, that's more of a different question. But anyway, and then you can also, okay, I'm running out of time, but you can also use the Hilbert transform to compute a phase analysis from the data. Essentially, yeah. Okay, this is the data itself. Here you get the Hilbert transform, and then you can plot the unwrapped phase data or the face or the wrapped face data that as you wish. But yeah, so here from the MC Hilbert, you get this unwrapped one by default, and here you can see whether there's any leader-follower relationship, right? So this is the unwrapped the unwrapped angles, right? So of the face. So basically, if one dancer has been doing like this, and the other one is a little bit more slow, then one who will be the leader and the follower, right? The one that has more angle at a given point in time, then it's going to be the one that is the leader, right? Oh, sorry, the follower. Yeah, because there's more zero crossing, so it has been going faster. Yeah. So I hope this was more clarifying than confusing, and that. If you have any questions, I'm here, so please feel free. We are here. Please feel free to ask. And yeah, thank you.
I guess this is up on the GitHub as well.
Yes.
Perfect. And then people can find your email there as well.
Yes.
Wonderful.
Yeah.
Then they have a way. Thank you guys so much.
Thank you.
We're 8 minutes away from the keynote by Martin Clayton upstairs.
Awesome.
Thank you so much again, Martin.
Thank you.